So let's start with a quick summary of whatever we have seen until now. So starting with the first thing that I just hope you guys have been working on is the Twitter project, right? So that was like a homework. Conceptual wise, we have been focusing on embeddings since the previous couple of classes. In embeddings also, we are specifically focusing on count-based embeddings right now. In count-based, we have multiple ways to embed, and we have discussed the multiple approaches, right? So if you remember, we discussed about a normal one-hot encoder, a binary vectorizer, right? One hot, or call it binary. Okay. We discussed about the count vectorizer. We discussed about TF-IDs. Okay. So all of these things will help you convert your text categorical columns into some numerical values. For example, wherever you have some text data, that will get converted into numbers. And that's the main thing which machine learning wants, right? Because numbers is what ML can understand. Now, we know that there were some limitations regarding this embeddings. Count-based embeddings are not fully 100% accurate. The reason being, they are, we convert the text into numbers based on the logic of count. We don't take into the logic of meaning. We don't take into the logic of context, right? And that is the main issue. Apart from that, we had discussed that there is sparsity present, and there are a lot of dimensions, like a lot of columns. Whenever we try to create that document term matrix, right? Because you will have a lot of words. Are we using GenSim library today for Word2Vec, Morris? Yes. So we are going to use GenSim library. We'll see like if we can cover it today or we'll be covering in the next one. But that's the main thing. So over here, we are going to discuss how we can overcome this particular challenges. Okay. So to start with, we know that the second type of embedding is the prediction based. And prediction based embeddings have one advantage, that they will take into account the context. Okay. They understand the relative words, what are the different words, they understand their meaning, and based on that, they will try to will try to convert them into numbers. Okay. So the beauty of that is, if you have two words which are similar, for example, let's say joy and happy. As a human, I know that they are same, like they imply the same, right? So we won't want two columns created for joy and happy, right? I wouldn't want that, because I know that I can save space by just combining them because they are same words. So either I can keep joy or I can keep happy, and I can remove the next column, right? But in count, we can't detect that. In count, both of them will be having different columns and both of them will have different counts, right? How much number of times they occur in the document. But in prediction based, we can understand that joy and happy are together, and we can just use joy, let's say, as one unit, and based on that, we encode it. Okay. Good. So let's start with the first prediction based embedding method, which is Word2Vec, and I think everyone tries to prefer Word2Vec only. So we'll probably start by discussing why people love Word2Vec. Okay. So Word2Vec, as the name says, you convert text data into a vector form, into numbers. Okay. The only difference is here you will be using machine learning. You will be using predictions. Okay. More specifically, you will be using deep learning. Okay. And using this predictions, let's see how we can convert that. Okay. Cool. Anyone is asking anything? No, right? Oh, okay. So now let's see one example of this. So let's say, mm, okay, let's say there is Virat Kohli and there is Rohit Sharma. Okay, let's say this two names are occurring in documents. Okay, some documents may these two names are occurring. I want to see that how is the relationship between both of them. Okay, between A and B. Let's say this is A, this is B, right? I want to see what is kind of relationship A and B have. Okay, so for that, in prediction based embedding, I will get some kind of output which we are going to discuss, using which the vectors will be close to each other. Okay, so what will happen? This is A, this is B, right? A is Virat Kohli, B is Rohit Sharma, and both of them will be close to each other. Let's say there is another, which is probably, let's say, probably, let's say, Sunil Chetri, who's a footballer, right? Let's say that person is C. Comparatively, we know the distance of Sunil Chetri and Virat Kohli or Sunil Chetri and Rohit Sharma will be a little far. Okay, probably C will be over here, right? So what I'm trying to tell you is the documents will have words Virat Kohli and Rohit Sharma almost in similar places because both of them are very similar. Like they come from cricket, but whereas the person Sunil Chetri comes from football, right? So the person will be a little far. The common thing between all of them will be sport, but if you see the angle between them, the angle between A and B is smaller. Between A and C or B and C will be comparatively higher than A and B. Okay. Okay, so using prediction-based embeddings, we'll try to find out this information and see how we can embed it in such a way that we get to see that Virat Kohli and Rohit Sharma are close to each other. Is Euclidean distance used to calculate distance? Euclidean distance suffer whenever we have more number of dimensions or columns, right? Uh, for example, let's say you will be doing x1 minus x1 minus x2 whole square plus you will be writing the next dimension, which is let's say y1 minus y2 square. Next, you will be writing z1 minus z2 square. Next, you will be writing, let's say, a1 minus a2 square. Next, you will be writing b1 minus b2. Imagine if you have 10,000 columns, you will keep writing this 10,000 times, 1, 2, 3, 4, so on for every single column, right? And now you'll be taking an under. Okay. The thing with Euclidean distance is if you keep doing the squaring so many times for each so many number of columns, the complexity of running Euclidean distance becomes very high because you will be doing this processing on 1,000 columns or 2,000 columns, which is not a good idea. And one more thing, Euclidean distance is never meant for high number of columns. The reason Euclidean distance was built was to just faster process some mathematically small tables, not the higher dimension tables. So the thing which we use in NLP is mostly cosine similarity. Okay. Cosine similarity works very well for categorical data or textual data, where they know that you have converted the text. I mean, they obviously don't know that you have converted the text into numbers, but it is meant for those scenarios where you have high number of dimensions. Okay. So since text, whenever we convert to numbers, you will most probably have high number of words as columns or dimensions. Cosine similarity can be a very good choice. Okay. So Word2Vec was officially launched by Google. Okay. This was officially launched by Google, and they basically created this as a patent for their own research. Now it's publicly available. So it's obviously a very good improvement over the traditional methods like bag of words, matrix, document term matrix, and TF-IDF. This is highly powerful. Okay. The reason why this is powerful is because it understands the meaning. Okay. It understands the semantic meaning. Semantic means it understands the context of the sentence. Okay. So it will understand like joy and happy are similar word. Okay. Similarly, let's say another advantage of using Word2Vec is with sparsity. So the output of Word2Vec will be a dense matrix. Okay, you won't get a sparse matrix as we were getting in the count-based approach. Okay. One more thing, it's going to be dense and also it's low dimension. Okay. So you would, instead of having, let's say, 1 million words as column, you probably have around 200 words, 300, 500 words. This is still fine compared to what you would have bought with count vectorizer, right? So comparatively, if it's low dimension, it won't suffer from curse of dimensionality, and storage wise and processing wise also it will be faster. Okay. The issue with like sparse vector is like if you have a sparse vector, it will have a lot of zero, right? If you have a lot of zero, this can provide a lot of unnecessary information, like a lot of noise will be there, which is not needed. And because of that, you have chances of overfitting on the data. Imagine like 90% data is all zeros, right? Model will unnecessarily try to think that, okay, maybe I'll have to focus on zeros. There are hardly ones, and that may just bias your model, okay, which is what we don't want. With dense, we know that there are very like whatever is the main relation that is there, unnecessary zeros are not there, and because of that, model will take care of overfitting. Okay, so one more thing, it uses deep learning. Okay, so we'll see what models it uses in deep learning. I know you have already covered deep learning, so you should be able to pick it up. Okay. So in Word2Vec, there are two variants. One is your pre-trained model. One is your current train, like you have to train it, self-train. Okay. Have you guys worked on any pre-trained model until now? Have you guys worked on any pre-trained model until now in deep learning or in machine learning? Have you seen anything like that? No? Okay. So pre-trained model means pre-trained mean, as the name says, that it is already trained. So for example, a lot of companies, for example, Microsoft, have already trained a model, built a model using multiple information. Okay, like multiple data sets, they have combined it to create a ML model. And now people can directly make use of that model predictions. I don't have to again train it. I don't have to care about uh, how is the training accuracy if I have trained the best model. It's already trained in the best manner possible, and it would give you pretty fast results because you don't have to train it once again. Same thing has happened for Word2Vec. Company like Google has already trained the model on a huge chunk of data. Like imagine in NLP, you would have so many words, right? How would they understand that, let's say, two words like joy and happy are similar to each other, right? So the reason is they have already trained it on so many English words that the model recognizes that joy and happy are having same words, because that kind of training has already been done. So now when you try to use pre-trained model, I won't care about training this particular Word2Vec once again. I can simply apply Word2Vec to transform the data into sentences. Whatever text I have, I'll just transform into into embeddings. And the best part is it will by itself take care of the scenarios where it will understand that, hey, these are similar words. Okay. The second option is a self-train. So this is where you want to add your customization. Okay. Let's say you want to train your own model. The only sensible reason why you should be using self-trained over pre-trained is, see, if you're trying to do simple analysis using some simple words which are very similar to, let's say, joy, happy, or any common English terms, right? Why would you again train the model, right? You already have a pre-trained model which has some decent results. Why would you waste your time in training it once again, right? So I won't use it. If my task is to use, let's say, common English words, I probably would use the pre-trained model. It will save my time. I don't have to worry about training, and I can directly utilize the predictions. But let's say if your end goal is to do classification or do some clustering based on data or based on words which are not commonly used in English. For example, let's say there are some maybe English abbreviations. Like, for example, let's say there are some, majority of your data has some abbreviations, which are, let's say, Gen Z abbreviations. Okay. Like, what is the term for that? People have this Gen Z abbreviations while texting, right? For example, talk to you later, talk to you later, right? And there are many others, right? For example, recently now, a lot of new others have been created. So let's say this kind of abbreviations are existing a lot in the data. Okay. And let's say there are uh, some more things which probably are not by default created in English language, but they have been created by people because of, like, personalization, just for customization. They have created all these words and phrases like talk to you later, and maybe you can just imagine few things which people might be using on chat, like for example, sweet dreams, and there can be many others. So over here in English, by default, let's say it, if, I mean, this is a very simple example, let's say, but if you have a more detailed Gen Z example, that would not be present in the first part, like in the same pre-trained model, because there it's trained on, let's say, common dictionary words. These words are something which are phrases, right? These are something which humans have created. I mean, that also human has created, but this is something which people have created by themselves on their language, conversation. It's not officially documented anywhere. Okay. Yeah, even goat, right? For example, if you write goat, now goat is greatest of all time, right? It's something which people have customized and given a title. Okay, with pre-train it will understand the animal goat. With self-train you can make it understand that there is an animal, and also goat is referred as a phrase to refer someone who's greatest of all time, right? So if you have this kind of use cases where you have to deal with vocabulary which is not directly present in your uh, common language words, like English, may it's not present in common dictionary, go with creating your own model. Okay, you'll have to train your model by yourself. Okay, that's why the self-train part. Okay. So in our case, we'll start with pre-train. We don't have to go into self-train because we'll start with an example where we are focusing on common English words. Okay. And even in industry, majority of the times you'll be using pre-trained only. Okay, because majority of the use cases are going to be in English language, and obviously with English language you will be obviously having information regarding the existing words, right, in pre-trained model. For example, in one of my project, I was looking into customer reviews, like how we have reviews on Amazon website, right? Similarly, I was working for a Fortune 10 client. For that particular company, we used to check their online reviews, okay, like reviews and also their complaints. And based on that, we used to decide like what kind of support we need at call center. Like if we see that there are high number of complaints, we'll probably try to hire more number of people at call center, right? So that people can handle the complaints. Okay. But how can we do it? We need to understand what type of complaints are there, because we need experts in different areas at call center. For example, let's say one expert will be in electronics to overlook the electronics operations specifically, because it's a very big company, right? So they will have many products in electronics. One I can have, let's say, for apparel, right? So I need to understand how is the complaint volume in different category, right? And for anyone to automatically classify whether the complaint is in electronic, is in apparel, I can simply, instead of using a human, I'll simply use machine learning, more specifically NLP, right? And through NLP, I'll classify the ticket as, a category, and according to the category we can check the volume in each category. Let's say in apparel the volume is very high, so what will I do? I will add more customer uh, call centers people over here. The staff will be higher over here to handle the volume. Okay. Okay, so this we used to do using Word2Vec only, because the complaints will contain English words. Generally, you can have people having like little bit of slangs because they are frustrated, or some slow words which are used, but that is fine. Like if it's not too much, that's fine. So Word2Vec will still give you decent results. Pre-trained one. Okay, I'll take a pause to see if you have any question. Okay, any question, guys? Okay. Um, cool. I guess there are no questions, so let's proceed forward. Okay, let's go a little deeper into how Word2Vec uses predictions. Okay, like how does it work? Okay, so to discuss the working logic, we'll take an example, and using that example, we'll see like how we can understand this. So let's say if we have few keywords. Okay, so let's say the few keywords that we have are, mm, let's say first one is tiger. Second one is, let's say, engineer. Third one is, let's say, doctor. Fourth one is, let's say, movie. And fifth one is, let's say, flower. Okay. Now, let's say we have some more words in corresponding rows. I'll explain what is happening. So let's say over here you have living. Let's say you have rich. Let's say you have healthy. Let's say you have maybe let's say interesting. Okay. So in rows, there are four words: living, rich, healthy, interesting. In columns, there are five words: tiger, engineer, doctor, movie, and flower. Okay. Imagine like you are checking, you are going to check, you're going to, let's say, create Word2Vec of different words. Okay. For example, let's say you want to create Word2Vec of living, you want to create for rich, for healthy, for interesting. Basically, for every word, you want to get what is the corresponding representation, right? That's what we want to get. So imagine if we can bring the data in this kind of form where we have some words in columns, we have some words in rows. Okay. And using this matrix, we try to give some numbers. Okay. So this is what is the starting point of Word2Vec. Okay, we'll discuss how we'll bring it into this form. It's very simple. We'll make use of the code to simply convert the, like, we'll simply do the pre-processing of the words, and we'll just split it into rows and columns. Okay, so you will have some words in rows, you'll have some words in columns, and you'll try to get a combination using all these words. Okay, we'll discuss regarding the split once we go into the code. But for now, assume like this is an example. Okay, this is the kind of words that you have in columns, and this is what you have in rows. The main logic of what Word2Vec says is you try to understand the meaning, right? Because Word2Vec already understands what is the meaning of living, what is the meaning of tiger, right? And based on that, it will try to give some score. Okay, like what is the score, which is like a similarity score between living and tiger based on their meaning. Okay, so since it understands the living word implies something which is, something which is breathing, tiger is some animal, right? So what is kind of relationship between them? Can we say tiger is a living animal? We can say that, right? So I'll say probably the score between range of 0 to 1 is probably around 0.6. Okay, living tiger, because tiger is a living organism, so you can expect in documents that tiger and living may occur together. Engineer and living, yes, that also can be possible. It may be around 0.7, right? Engineers are also like living, let's say, a lifestyle or living a healthy life, something like that. Same thing can happen for doctor as well. Movie, living, do you think this combination can occur a lot, movie and living, right? This is rare, right? Movie and living don't seem to probably have similarity. They don't seem to, exist together. And that is why we'll probably have a lower score for movie and living. Okay, so let's say probably 0. Similarly, flower and living can have a decent score because flower is also like a living animal. I mean, living species. Okay, so let's say this is around 0.4. Okay, so what you noticed, we are giving scores based on the meaning of it. Same thing with rich and tiger. Do you think rich tiger is something which can occur probably a lot? Maybe not, right? Rich is probably for human. Rich and engineer, yes, this probably can occur. Rich doctor, maybe it can occur, and it may occur a lot number of times. I'm just giving a very high score. Rich movie, maybe not, right? So I'm giving it a 0. Rich flower, maybe not, 0, right? Now, healthy tiger, yes, that can also occur. Let's give it 0.9. Healthy engineer can occur. Let's give it 0.7. Healthy doctor can occur, 0.9. Healthy movie doesn't seem to occur. I'll keep it 0. Healthy flower, very less, I would say. Like generally, we don't say the word healthy flower. Okay. Interesting tiger can be there. a little like low frequent, because interesting tiger is something which like I don't think so we'll probably say a lot of times, right? We say tiger is beautiful or tiger is the large animal and all, but we rarely would say tiger is an interesting animal. Interesting engineer, maybe we can use. Engineers are interesting people who keep inventing so many stuff. Interesting doctor, maybe, right? Doctors can also be equally interesting. Interesting movie, I think interesting movie is probably the highest, right? You have a lot more chance of saying interesting movie. Similarly, interesting flower, I don't think so we say interesting flower, I'll keep it 0. Okay. So we are trying to give scores. This is what the machine learning model will try to do. Okay. It will try to give scores based on the meaning of the words. Okay. It will try to understand what are the corresponding words implying. And based on that, it will give this kind of scores. The best thing is these scores are given by meaning. Okay. It's considering the meaning. And based on that, it's trying to give the different scores that we have. Okay. So from this, if I ask you what is the representation for, let's say, tiger, okay, you can simply give me the encoding, which is this, okay, the column value, right? So you'll see the representation for tiger will be 0.6, 0, 0.9, and 0.3, right? I get a vector. Same thing if I ask what is the representation for interesting, right? You will give me the entire row, right? So I get for interesting the representation. So are you noticing that over here we are having the representations in numerical form, or this is in vector form, right? We are able to convert based on the meaning. Okay, let's go a little deeper. Let's try to understand what else is going to happen over here. Okay, so coming to the point now, how does that happen, right? How is it giving the scores? The scores are very similar to like probability, right? Very similar to probability. And to give out probabilities in the backend of Word2Vec, we are going to use neural network. Okay, we are going to use neural network, which is what is the main driving logic behind creating this probability. We'll talk about the architecture of neural network in few minutes, but we'll create a shallow neural network. All of you understand a shallow neural network, like not a deep neural network, right? Something which doesn't have a lot of layers, right? You guys have studied neural networks, right? Have you guys studied neural networks? Can you type in a one if you have? Okay, so I guess you all of you understand the meaning of deep neural network, shallow neural networks, right? Okay. Okay, so before we go into the architecture, let me actually show you a couple of diagrams. Just give me a moment. Uh, okay, so in this document, this is a very famous project on Game of Thrones, but we'll go into the code a little while. But if you notice this diagram, okay, this is a heat map where you have basically information regarding Game of Thrones characters. You can see like Jon, Sansa, and you'll have all the set of words. For this set of words, you'll have corresponding vector representation as how we created the vector representation, right? So for every word, you have the respective vector, 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 vector representation. And based on the score, like if two have a score which is very high, like 0.9 or something, right? The heat map will show a darker color for them, right? Let's assume that. So using a heat map, you can identify which words are probably similar to each other. Okay. For example, let's say John has 0.3, Sansa has 0.3, 0.3, 0.3. I will have a similar color for them, right? So it tells me that probably these words are quite similar to each other. Okay. So using a heat map, you can simply visualize the scores and the vector form of the different words. Okay. This is nothing but the different words. They have just encoded the words in number forms. Okay, let me actually show here. So basically you have, let's say, tiger, right? And you have the scores. Just a second. Hey Siri, kindly lock my screen. Thank you. So now you have tiger, you have interesting, you create the representation, you color code them using a heat map, and that's how you will get to see the relationships. Okay. So Word2Vec has different types. Okay. There are different types of Word2Vec which we'll see. The first type is a CBOW, which is continuous bag of words, and the other one is skip gram. Okay. These are the two types which exist for Word2Vec. Okay. So there are two variants of Word2Vec. We'll see like how do we implement them. Okay. This is a continuous bag of words. Okay. Skip gram we'll talk about just in a while. Okay, let's start with the first one, which is CBOW. So C bag of words. Okay. So in C bag of words, we create the numerical representation, right? The vector form by starting with a dummy data, by starting with a dummy problem. Dummy problem implies a problem which doesn't exist. Okay. So we are taking an artificial problem. We are taking a problem which is not existing only. Okay. So what we'll do is we'll create a dummy problem and we'll try to solve it. Okay. I will explain like why we are doing it. So we'll create a dummy problem. We'll solve it. Okay. And by solving it, we'll get a vector representation. Okay. And the output of this vector representation is what will be the numerical representation. Like this itself will be the numerical representation. Okay. So let's say um, do meditation every day. Do meditation every day. Okay. Let's say this are, or let's probably add one more. Do meditation for a week. Okay. So this is one sentence in which you have one, two, three, four, five, six words, right? Do meditation every day for a week. So now in this sentence, let's see how we can use CBOW to represent it in the numerical form. Okay, so now what we'll do is we'll start with the fake problem. Okay, we'll start with a dummy problem. We'll define how many number of dimensions we want. Okay, this is like a hyperparameter. You can define any number of dimensions that you want. Let's say I am defining, I want to represent it in 3 dimensions. Okay, so first step is to decide a arbitrary number of dimensions in which you want to represent the data. The more number of dimensions, the better it is. This will be a hyperparameter. But again, too high can also be harmful because unnecessary you will be increasing the dimension, which will increase the size, which will cause curse of dimensionality issues. Okay, so we'll discuss like what is happening with this. But first thing, we need to decide some dimensions. Let's say I say that keep 3 dimensions. Okay, now, what does this imply? This implies that we will be representing the whatever the words that we have, we'll try to represent them into 3 dimensions. Okay, let's say 0.9, 0.8, and zero point 0.1. Okay, A, B, C are the dimensions. Okay, so the main logic of continuous bag of word is to follow a continuous approach. Okay, continuous approach means it will follow a window. Okay, so after defining the arbitrary dimensions, the next thing is to define what is your window size. Okay, so let's say I define my window size is 3 units. Okay, it's 3 units. So what does that mean? So let's say if I say my window size is 3 units, it means that I would be taking three words and moving in this sentence, which means I would be taking first 3 words. Okay, these are the 3 words that I'll be taking. And in this, the middle word, okay, whatever is the middle word, will be considered as target. So meditation will be called as the target word. And the rest of the 2 words will be called as independent words, or let's call it as context word. Okay. This is also a context word. Okay. So target is the center word and it's a target word. So first time this will happen. Next time when you move ahead in the circle, let's see, now you will go to meditation every day and for, right? This time every day will become the target. The rest 2 words, which is meditation and for, will become context words, right? Same thing will happen when you move one more step ahead. The next time, what will you have? You will have every day, for, and right? Assuming you have not treated the stop words. If you have treated the stop words, and for will get removed. So over here, for will become your target, right? So you will keep doing this till you terminate till the end of the sentence. So you are defining a window size. Using that window size, you are moving ahead and getting the target word and you are getting the context word, right? That's what you are getting, okay, every time. So let's say the first iteration, second iteration, third iteration, and so on. You'll keep storing what is the target, what is the context. Okay. So basically, you will be defining target, which is your y variable. Okay. And you'll be defining context, which is your x variable. So now we are going to frame this in a machine learning problem, right? You are having y and you are having x. Okay. So for example, let's say in the first iteration, do and every day were context. So let me write do and every day were context. But the target in the first iteration was meditation. Okay. Similarly, second time the target became every day, right? So I'll write every day. And context was every day and meditation. Sorry, context was meditation and for. Okay, and we'll keep doing this till the end of the sentence. Okay, I won't write complete thing for now, but once we have all the target and the x variable defined, now this is ready to be taken as a ML problem. Okay, we will see like how we want to handle this. So what will happen is we'll use this information in form of a neural network. Okay, we'll try to create a neural network by like inside Word2Vec is what a neural network will try to do. Okay, as we know, this neural network is what will ensure that you are having the proper set of numbers. So the architecture of this neural network would look something like this. The first layer, the input layer, will be the number of words that you want to give as input in the sentence. Okay. So in the sentence, we have 1, 2, 3, 4, 5, 6, because I want to convert the 6 words into the numerical representation. So I need to have 6 input. Okay. So let's draw 1, 2, 3, 4, 5. Okay. Just give me a moment, guys. I need to take up a call. Just a minute. Okay. So over here, you are having 1, 2, 3, 4, 5, 6 input layer, right? So you have 6 units, 6 neurons triggering in the input layer. Okay. Why 6? Because each one we can pass one word. Okay. Now what will happen? We will have a middle layer. Okay. Middle layer as in your hidden layer, where you will be having the weights computed. So over here, this middle layer will be defined by the number of dimensions that you decided, right? So you said you want 3 dimensions over here, right? So this 3 dimensions will be present over here. 1, 2, 3. Your A, B, C. Okay. And now after this, since it's a shallow network, you will directly have a output layer. Output layer means in what number of dimensions do you want to represent the answer? Okay. So let's say I want to represent the answer in 4 dimensions. Okay. So I will specify 4 as the output. So my final answer would have 4 dimensions as the representation. So what will happen? You pass all the words. And by the way, this is a like fully connected network. So each one will be connected to every other neuron, right? So this will be connected, this will be connected, this will be connected, this will be connected, and so on. Okay, you can imagine the net. So over here, I'll pass all the words one by one, one by one, one by one, one by one. Each word will get converted into a dummy problem, okay, in a fake problem, which is a temporary problem, okay, where we have defined the arbitrary number of dimensions as 3, okay. And to convert that, we'll see like how that conversion happens, but it will convert them into some kind of problem by computing the weights. Okay, it will compute the weights, and based on that, we'll finally have a final output given by, let's say, some kind of output function, right? We need the final output function, which will use sigmoid. Okay, we can use sigmoid function as the final, or let's use softmax. Okay, so now what will happen? The final output in softmax over here, again, like this will be connected 1, 2, 3, 4, 5, right? And similarly, the rest of the 2 also will be connected to everything, right? And this layer, we are using a softmax function so that we can generate the probability values. Okay, so now what will happen? Over here, you have how many? 6 into 3. 6 input, 3 intermediate neurons. Over here, how many you have? You have 3 over here, you have 5 over here, right? So you have 3 into 5 weights. Okay. So now what will happen? We know from our understanding of neural networks, how does neural network work, right? You will pass it in epochs, right? You will pass it in steps, in iterations, right? So with every single epoch, right, what will happen? Each word will get passed. So let's say the first word, which is, so let's say do, okay, do. So do will be passed, okay. And next you have meditation, okay, and so on for everything, okay. Do meditation every day for a week. Okay, all these words will be getting passed. Now, the neural network will try to represent this into 3 dimensions. Okay, and based on that, based on how it's going to represent it, we'll see a output for every single representation. Okay, like for all of them, we'll get to see like what is the best thing that we can combine. Okay, so let's say you get an output over here, which is, let's say, integers. Okay, let's say 0, 0, 1, 0. Okay, This are the different outputs which have been computed, and obviously I can see the probability values as well. Okay, but this may not be fully accurate. So let's say this is when I passed meditation, I am getting 0010. Okay, this is what I'm getting. Now I will pass every day. When I pass every day, let's say I'm getting 10000. Okay, let's say this is what I'm getting when I pass every day. Similarly, I'll keep passing the rest of the votes. Okay. The thing with neural network is we use back propagation. Do you guys know back propagation? You guys have studied back propagation, right? Can anyone confirm in the chat if you have seen this? Okay, cool. So what this back propagation will do? As soon as you pass meditation, it will arbitrarily create a random representation of it, because you are randomly saying, create 3 dimensions of it. And after that, it will show you a representation. Okay, you will compare this representation with the original representation. Let's say you have training data. In that training data, you can see the original representation should be 1010. So you can see like 0010 and 1010. 3 numbers are correct, 1 number is misplaced, right? So loss will be computed, right? Because back propagation works on the logic of loss. You'll compute the loss, you will see if the loss is high or low. In this case, the loss is low, right? Based on its working, the neural network will try to reduce the loss. So it will try to reduce the loss, it will back propagate. Okay, right? It will go over here. From here, it will go over here. Right? Back propagation will happen, and with different epoch, you should see a different result. Like the loss with more epochs, ideally should reduce, right? Because of back propagation, you'll get more optimized output, and because of that, the loss will keep getting reduced. Okay, so in a way, at the end, once all the epochs have been completed, you have reached a stable stage, you will see an output which is very close to what you are expecting, like 1010. Okay, this is when we say like this has been properly trained. Okay, so obviously the main thing over here is the weights, right? This weights that we'll have, we need to ensure we have the best set of weights, right? Because if you have something which is not properly defined, if you can't adjust the weights properly, or let's say you don't specify the hyperparameters correctly, a lot of things can go wrong with the weights, and because of that, your representation can mess up. Like you won't be able to get a high accuracy. Okay. Okay. So this is input. You pass, let's say, meditation. An arbitrary or a dummy representation is created. Using softmax, we'll try to convert it to probabilities. You will get a representation of meditation. This is the entire representation, which is for meditation. Okay. Now I'll do it for every day. I'll get a representation for every day. I'll get it for, and so on. Like you pass all the words and you'll get different representations. Okay. Good. So I can actually create a neural network architecture where everything is happening in parallel, right? For example, let's say um, you pass all of these things as input. Okay, and let's say I want to see, okay, let's say 1, 2, 3, 4, 5, 6. Okay, you pass all the 6 together. Neural network will try to understand the relationships between all the words, and based on that, it will create an arbitrary representation, uh, which we have defined, keep it as 3 units. Okay, and obviously the first word will try to get connected, this will get connected, this will get connected, will try to see, understand the relationship. I won't go into the very deep principles of neural network, but you'll get to understand the different relationships which are existing. And now while giving an output, let's say I want to pass I want to get an output for the word meditation, okay, and for the word for. Okay, so I can actually create the output in parallel. Like let's say I want to represent the output in 4 neurons. So I will say 1, 2, 3, 4. Okay. Tuck, tuck, tuck. This is a representation for meditation. Okay. Similarly, 4 neurons for the word for as well. So I'll simply add 4 neurons over here. 1, 2, 3, 4. Okay, and I'll connect this, and this. Okay. Same thing will be connected with this and this as well. Right? This is for for. Okay. So let's say for the representation is 1, 0, 1, 0. For meditation, the representation is 0, 1, 0, 1. Okay. And now for different words, you can get the representation in output. Okay. And that is the main logic of continuous backward words. You are creating the words based on neural network. Okay. So whatever words that you are passing will get computed according to this architecture. Okay. So for every word, you can represent them in number form. Okay. So obviously the training time will increase compared to a count based approach, because in count you simply have to count. Here you have to build a neural network, so train time will increase if it's not pre-trained. Okay. Second thing is regarding hyperparameter. You need to control few hyperparameters, so you need to control the arbitrary dimension that you're passing, right? The middle dimension, the dummy problem that you're passing. So you should not have it too high, you should not have it too low. Having it too high will increase the computation, like will unnecessarily have a lot of sparse data created, because let's say if you can represent the data only using 5 neurons and you're passing like 10 neurons, there's no point in it, right? Because unnecessarily you won't be having any information in the extra neurons. Second thing, you can't have it very low, because let's say if you actually need at least maybe few neurons, maybe like 5 to 10 neurons to capture the information, then you need to pass that minimum number of neurons. If you pass too less neurons, it won't understand the complete context, it will underfit. Okay. So there should be a proper balance. First thing. Second thing is the window size is again a hyperparameter. We considered a window size of 3, right? Where we consider pre, current, and post, the target and the context. But you can increase the window size to 5 to 6 according to you. Okay, it's again a hyperparameter. If you increase the window size to more number of words, you will try to get relationship between continuous word. Like instead of taking unigrams, you can have bigram. Like for 3, you are taking two words combination. If I increase it to, let's say, window size of 5 units, right? What will happen? 5 units mean one word will be target, 4 words will be context. So I will get to see relationship between 4 words, A, B, C, and D, right? So you can play around with this. Okay. But obviously, if you increase it too high, like if you say the window size is equal to the number of words in the sentence, like if you keep a window size is 6 units, what will happen? You will have only one window, right? Because all the words will be covered in one window itself. There is nothing after that. Okay. So you should not have like too high window size as well. You should not have too low window size as well. You should have something in between. Okay. It's again a hyperparameter. Okay. Obviously, as it's a neural network, you will not have feature importances, right? You would not understand which words are important because modern explainability doesn't exist. Okay. And that's a limitation. Okay. So this is a limitation that you won't be able to see that, hey, which is the most important word. You will be able to see the scores which says like which words are similar, but you really can't say like, hey, which is the most important word. Okay. So we'll see an example of this in practical. Okay. So let me open a project.
Can you share the link for Word2Vec, that Game of Thrones also?
Sure, sure. Okay. Okay, let me run this with just a second. Um, have you guys studied autoencoders? Do you guys know about autoencoders? One or zero? You would have heard this term probably in deep learning, autoencoders. Have you not?
Yeah, we have heard the term, but not explained in detail in deep learning.
Okay. So you don't know the working of autoencoders? Is that right to assume?
Yeah.
Okay. So then let's not look into this project. Okay, just give me a moment. Okay. Just one last thing. I forgot to cover the last topic. Before that, okay, let's cover this topic and then let's go to the code. Okay. So we saw continuous backward words. Okay, but we didn't saw skip grammar. Okay, as I said, there are two variants, right? For Word2Vec, one is a continuous backward word, which is what which we discuss right now, and another one is a skip grammar. So the only difference, it's very similar, okay? The only difference is in continuous bag of words, you are passing input, which are your words, right? Which are your words for which you want representation, okay? So over here, in your case, since we have, created this by taking the different context, so you'll pass the context words and you will get the target word as what you are getting, as for what you want to get the output. For example, if I want to check, okay, this is for continuous bag of words. If I want to check what is the representation for meditation, right? I will pass do and every day, right? As we discussed, this is your X and this is your Y, right? So that's what we are passing. You'll pass do and every day, right? You will trigger the neurons of do and every day. You won't trigger everything. And you'll get the representation for target meditation. Okay. So here you are predicting. Yeah, let me just write, just predicting the target using context, where what target and context implies that you are predicting the current word in the window, which is your target, using its neighbors. Is that right? Right. That's what we are doing. We are using the neighbors of the current word to predict the current word, right? So to predict meditation, I'll use do and every day, right? That's what we are doing. And over here, what will I do? I'll simply, if I want to predict for meditation, what is the representation? I will pass do and every day, and it will give me a representation of meditation. Okay, that's one thing. In other case, whereas skipgram, the opposite of that will happen. Okay, in skipgram, you will predict you will predict the neighbor, all the neighbors, okay, however neighbors you have, like if you have two neighbors, four neighbors, or so on, using the current word. Okay, it's completely opposite of it. Okay, so which means what sentence you had do meditation every day for a week. Right? This was the words that we have. And now using a skip graph, you will do the reverse thing. You'll again have the window size and everything else like will remain same. But only thing is your target and your X variable will change. Okay. So now, for example, let's say first iteration, you take 3 words. Okay. Meditation is the current word, right? But over here, the target and current word will get replaced. Okay, the target will be do comma every day because you have to predict the neighbors using the current words. And over here, the context or the X, this is Y, will be meditation. Okay, you're switching the words. Okay, that's it. Now, when you move ahead, you will have meditation every day for. So accordingly, every day will become your context. Okay, and what will you predict? You will predict meditation and for. Okay, meditation and for. Okay, that's the only difference. So in the representation of it, you will also see accordingly. Like in this example, how would the neural network would look like? You will pass the X variable, which will be similar to how you would imagine. Like you have the list of words, whichever you want to trigger at a point. Okay, you will have intermediate representation, same as how we had in continuous bag of words. And now you will have the representation for output. Let's say if you want to see the output for meditation, I will have, let's say, 4 units represented for meditation, 4 units represented for. Okay. It depends on what you're passing. The neural network architecture is almost same. Only difference is with what you're passing in input and what you're getting in output. It's just flipped out. Okay. Like one, you're passing X and you're getting Y. Another one, you're again like passing X, but it's opposite of what we had passed in the continuous bag of words. Only because the definition of it is reverse. Just one thing. Majority of the times in NLP, we use skip graph. Okay, we use the logic of skip graph. Skip graph works better for huge data. Okay, whenever you have a very high size data, okay, large data, prefer skip graph. Skip graph will give you much more better results. Okay. Okay, let's see this.
The logic is reverse. What exactly is that?
So what we were defining as target in continuous bag of words is now defined as context in skip graph. Did you get it, or should I? Do you want me to explain?
Means you have two variables modulating to one. How the equation will be framed here? Do everyday meditation.
Okay, so this is where you have multiple output, right? You are going to create one for do, one for every day. So what will happen in the neural network? You will have one representation for do. We are representing each output by 4 dimensions. So this is going to be 1 dimension. And similarly, you will have another dimension for every day, like again 4 dimensions for every day. And now the architecture will remain exactly same. Like you will have all this connected and all, and this connected, this connected. The neurons will pass based on the weights that you're given, right? And for every day, I will simply see what is the value for this. Okay, just connecting the neurons, I can see the equation. Okay, so if I were to add, let's say, a bigger window where we are in output, we have one more word like do every day and meditation as well. What will happen? I'll add one more dimension in the output for 4 units, 1, 2, 3, 4, which will be for meditation. Okay, let's see this. Okay, so this is a simple example. Okay, so you are passing inputs which are sentences You apply Word2Vec, you get the vector representation as the output, right? That's what is the job of Word2Vec. It represents everything in form of your vectors. Now let's see how does this work. There are two types, CBOW, continuous bag of words, and the skip graph. Okay. So if you see the working, given a set of sentences, the model looks on the words of each sentence and it tries to use the current word in order to predict its neighbor. See, use the current word in order to predict its neighbor, right? So here you are predicting the neighbor, right? Neighbor can be multiple, and that is why it's skip graph, correct? If I reverse this, it becomes a continuous bag of words where it uses each of the context, that means each of the neighbor, to predict the current word. That is called as continuous bag of words. Simple. That's what we discussed. And now over here to decide, like there is a hyperparameter which is your window size. Okay. You can look at the examples. So this is your window. It's more like this is the sentence: the quick brown fox jumps over the lazy dog. And with this sentences, you are defining like multiple windows. Okay. All these are different examples. This is not part of the same training. Okay. Here window size is 3. Here is 4. Here is 5. Uh, here also is 5, but it has moved one step ahead. Okay. So all of them are different examples. Okay. But one thing, do you know what is the unique thing about this sentence? The quick brown fox for jumps over the lazy dog. Okay. The unique thing about this particular sentence is, anyone who knows? There's something special about this sentence in English. Okay. So the speciality of this sentence, you'll see this a lot of times in NLP. The speciality of the sentence is it's the shortest sentence which covers entire alphabets. You will have all the alphabets in this sentence. Okay. So just pick out any alphabet. M is there, Z is there, X is there, O is there. All the alphabets of English language are present in this sentence. Yeah, meaningful sentence, obviously. Okay, so Word2Vec vectorizes words and obviously it converts them to numbers. Using those numbers, we can find out similarities and all that using cosine similarity and all. Okay. Okay, so a neural word embedding represents a word with numbers. So basically, it's what we have discussed. Okay, this is fine. This is fine. Okay, so context to predict a target word, which is CBOW, or word to predict a target context, which is your skipgram. Okay, so now it's saying that we'll use skipgram because it produces better results on large data set. Okay, as we discussed, that skipgram works better for bigger size. Okay, so now look into the architecture of CBOW and skipgram. Over here in CBOW, you're predicting the current word, right? So you will pass the neighbors, like let's say WT is the current word. So you're passing the neighbors WT minus 1, WT minus 2, WT plus 1, WT plus 2. WT will not get triggered, right? Over here in skipgram, you are passing the input as the current word and you're predicting the neighbors, right? So obviously the neighbors will not get triggered. Only thing that will get triggered is your current word, right? And you're predicting WT minus 2, T minus 1, and so on. For each one of them, you'll have individual neurons representation in each of the rectangles. Okay. In both of them, the architecture is similar. In both of them, you will have a projection, which is nothing but a dummy problem, like a intermediate representation. Okay. So that like we need some, like, how does gradient descent work? You start with random allocation, right? You start with some random values for weights, and based on that, you keep optimizing based on the gradient descent, right, to arrive at the accurate weights. Same logic applies over here. We need something to start with, and that's why we start with a random projection. We create a fake problem, and based on that, we try to optimize it. Yeah, using backpropagation. Okay. So when the feature vector attained cannot be accurately predicts the words. Okay. So for example, let's say when it's not able to predict the output correctly, what will happen? The components of the vector will be adjusted. How they will be adjusted? Again, this is based on backpropagation. Okay. they will send the error signals back to adjust the feature vector. Okay, what is this? Sending the error signals back. What is the error? Like this is same thing as I was saying. You will check the loss. You will, according to the loss, you will adjust your weights. Right. Same thing as backpropagation. Um. Okay. 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 This is fine. Okay. Read this. So over here, the output of the neural network is a single vector, also with 10,000 components, containing for every word in our vocabulary the probability that it is randomly selected nearby word uh, nearby word is that vocabulary word. Okay, so it's saying the same thing only, but in form of different numbers. So it's saying that you will be getting the output, which is the target word that you're trying to predict using the neighbors, but instead of seeing like the representation, you can see the probabilities as well. Like if you apply softmax, you can get the probabilities, and you will get to see the probability, like what is the probability of the target word, like in this representation, what is the target word probability uh, if these are the neighbors. Okay, that's what you will get as the output, and that's what it's saying. Like it will represent this representation in form of every words, but it's not always needed to represent it in form of every words. You can represent it in limited words as well, like in limited dimensions. It's saying like if you have 10,000 words, we'll represent it in all words. Okay. Okay. So imagine in some way if we could label the dimension. Okay, like imagine a hypothetical scenario. Um, yeah, if I label the dimensions in a hypothetical word vector, okay, so obviously you don't have this predefined. Okay, we'll talk about this, but let's say if somehow you can generate, right, even in starting may I was saying you like consider if it's possible, like you have all these words. Okay, now my problem becomes simpler. I can simply get the meaning of different words based on Word2Vec. I'll convert them into the representation based on, hey, what is the similarity between, let's say, king and royalty? Like, what is the chance of occurrence? Okay. Okay. The explanation for that is given over here. So you can read about this, like, if you want to go a little in deeper knowledge, but most probably, I think you would have already understood this because then, like, only thing is regarding the neural network weights computation. Because you can see this mathematical computation of weights. It's simple, like a simple neural network. We know how it works. WTX plus B, that's the same equation which will apply over here. Perform the matrix multiplication, you'll get the answer. Okay, so I won't be going into the deepness of deep learning over here because our focus is on NLP. Okay, so see, softmax classifier has been added. The if it has been added, you can utilize it for getting the properties. Ta, 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 ta. Okay, this is like talking about the back propagation only. Like they use the chain rule to propagate the error, which is what we do in back propagation. This is all fine. Okay, in numbers, you'll get to see this kind of output. You'll see this equation, which is fine. Probability okay, you'll get the conditional probability, which you can get it from the neural network. Yeah. So if you want to understand like a little deeper by taking some examples, you can read this. Like there are 3, 4 notes which they have passed, and you can do the calculation. Like if you want to manually perform the calculation using a sigmoid function. Okay. In case if you are interested, it's not required. Like no one nowadays asks you to do that, but still, if you want to understand this, take it. Okay. Uh, so just a small snippet of the code. You will load the data. Like, okay, loading data is fine, assuming you have data in data frame. Okay, so you can tokenize the data. There's an option to tokenize. There's an option to pre-process. But the main thing is training. Okay. So this is not configured in Python. This seems to be some other language. Okay, anyways, we'll see a code for Python in the next class. Yeah, double. I think this is in system.out. I think this is Java, right? Hmm.
It's Java.
Yeah, it's Java. Okay, so we can see the Python example right now, but we'll probably see it in the next class when we build a proper project. Okay, so we'll compare in that project the word-to-vec representation with the count of words, and we'll see how much difference is in the performance. Right. So this is the main part. This is like the crux. Until now, we have actually covered the main topic. Okay. If you okay, let me switch back to the notes.
Can you share the link?
Sure, sure. So until now, the main part was understanding the embeddings, which we have covered. Okay, we saw an embedding based on count. We saw based on prediction. Prediction means there are like variations. I mean, there can be so many variations, so many algorithms. We obviously don't have to understand each and every single thing. If you understand word-to-vec, the others will seem like a variation of word-to-vec. Okay, so those things are a little self-exploration because we don't have time to cover each and every single algorithm, right? As how you would expect. But still, we'll see some more variations of word-to-vec in the next lecture. Okay, cool. So advantage is again based on the semantic, based on the meaning of the sentence, you are finding the similarities and creating the embeddings, which is much powerful than simply using the count approach. So we'll solve a classification problem also after that, and we'll talk about POS tagging because that's one topic which is left. Okay, so we have. So if you remember, I told you in NLP you will have input, which is text. You will have embeddings which convert the text into numbers, and then you have machine learning. There are two steps: one this and one this. One is regarding embedding. One is regarding machine learning. Okay, embedding one we have almost covered it. Machine learning one, you already know the algorithm, so there are like no new algorithms that you'll see. So we'll simply implement the algorithms. The working of the algorithms you already know. Like for example, you'll see logistic regression. I won't explain logistic regression, right? Because you already know this. So we'll simply implement logistic regression, right? For example, let's say there's another algorithm which you see is let's say DNN, right? Deep neural network. You have already learned about deep neural network, so I won't explain what is deep neural network. But you will simply apply it. That's it. Cool. So mostly by next week, by Wednesday, we should be able to wrap up NLP. We'll probably need 3 more lectures to build the projects. Yeah, and one topic which is remaining is POS tag. Okay, we'll see this in the next. Okay, we'll see POS tagging and we'll build a classification project. The Twitter sentiment analysis, that was one classification project that we have done, but we'll see using this thing, prediction-based approach as well. Okay, any question, guys?
MJ, I have a no, like I need a help actually. Like tomorrow, I'm having my PhD entrance exam at VIT University, Chennai. So along with that, I need to present a paper which I'm going to propose. Just an idea. I'm sharing that based.
Okay, okay, sure, sure. You can share it. Okay, so what exactly, where exactly do you need my help, Deepika?
Oh, sorry. Okay, like my proposal idea is like to do it in generative AI-based LLM models. So, like to just to differentiate from this to that, what I have planned to tell is like this we are going to do it in the large set of data. And one more thing I can differentiate is like this reinforced learning thing I can implement. Can you suggest like what else I can differentiate from this to change it to my idea to this generative AI LLM model? I have
Um,
only these 2 points to say them.
okay, so I would say like this is a acceptance round, right? Like based on your proposal.
Yeah. Based on this only, they will accept it. I mean, they will.
Okay,
I
okay.
have to enroll and yeah.
So any specific reason why you want Gen AI only?
No, like I actually it was a short notice, so I was not able to like search many things. So I thought like in this, I mean in this paper, the proposal was to do with large data. So suddenly when I search for, I can do with Gen AI LLM model. Only that idea I got. If there is anything
Okay.
you can suggest, also I can.
Yeah, actually, like in any field, even if we go with classical machine learning, we can do a lot of research work. But
Okay.
I think one of the place where you'll have abundance of research opportunities is reinforcement learning, in my opinion.
Yeah. Okay. Okay.
Because in reinforcement, a lot of articles, I mean, there are a lot of articles, but still as not as many research papers that you would expect for classical machine learning.
Okay.
So
Okay.
even with reinforcement learning, you can apply it at a lot of places. Like you just need some sample data from around you, and you can play around with it. There are like if you somehow get some supply chain data, or if you get some retail data, you will have application everywhere for reinforcement learning. You can use it
Okay.
for marketing. You can use
Yeah,
it
that
for
is what I
optimization.
had two options. Like one is for the Gen AI based LLM model, and one more thing, what I thought of that reinforcement learning with human feedback.
Yes, yes.
Yeah,
So
okay.
I
So
think, do you need to define the problem exactly, or you just need to write
no,
the
just
topic?
give an idea like what since it is the selection process, no, like what is our idea in which domain
Hmm.
I'm going to propose and such some basic ideas on what I'm going to do is enough, they told me, but I'm
Okay,
not
so
sure, like, so I just want to be aware like if some other questions if they are going to ask like how to handle it.
Okay, so I'll say you can go with Gen AI and LLMs also. There also are a lot of opportunities for you to explore. Like we can, focus on chatbots. We can focus on question answering bots, and we can focus on automated uh, this exam checkers. There can be a lot of apps that we can create. Both are interesting field, and I think if you don't want to exactly define the problem, we can make use of it. Utilize this
Okay.
website. Okay, the website name is Paper with Code.
Okay.
Do you know about this website, Papers with
No,
Code?
no, 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 no.
Okay, so check out this website,
Okay.
Papers with Code. Let me share it in the chat.
Okay.
So this is a website which is prepared for research people only. Okay, so you will
Okay.
get to see all the trending research, whatever has been done, and based on the stars, you understand which one are the most popular. For example, let's say if you want to search something on LLM, I'll just simply search LLM. Oh, wait, what happened? Sorry, I think this did not run. Yeah. So you have this task, LLM generated text decision, LLM
Okay.
real life task testable, and you
Okay.
can play around with it.
Okay.
The good part is here you will not only get to see the research paper, which is already created, but you
Okay.
will also get to see the code, like using what code the paper has been created. Like once you
Okay.
probably go ahead, you can utilize this repository.
Okay. Okay.
Okay.
Okay. Okay.
Yeah.
Thank you. Thank you, Anji.
Yeah. Cool.
Also, like, like I wanted to tell, like whatever is given in that base paper, like you have already explained it clearly, and it was easy for me to understand things. Like, thank you so much.
Oh,
So everything, like once you just read it, now every single topic was just explained by you already. Like this from the scratch, it is explained clearly.
oh, thank you
Yeah.
so much, Deepika. I'm really glad that this is
No,
something which
like
is
your
helping
your
you.
teaching is with IEEE standards.
Thank you, thank
Yeah,
you.
yeah.
Thank you. Okay, cool, guys. Thank you so much for attending till the end. I hope you enjoyed this lecture and wish you all the best, Deepika, for your entrance.
Yeah. Monday I'll
And
let you know whether I got
oh,
admission or not. Yeah.
okay, hopefully you get
No,
it.
like actually for MTech standard, I don't know like whether this topic is also
No, I
worth
think
for that.
definitely, I think it's worth it. Like
Okay.
because I also come from VIT,
Oh,
and
is it? Okay, okay.
yeah, so
Oh,
I was in the Vellore campus,
okay, okay. My
and
native is Vellore actually. Yeah. So, but
oh,
I
okay,
got settled in Chennai, so I wanted to do it.
oh, okay, okay, okay.
Okay. So
Oh,
obviously I got a guide. She's my friend actually. She's working there. So I thought like she said she can guide me. So
I see.
uh,
I think definitely like MTech wise also you will have a good learning opportunity, and I think the topics that you have taken should be much more
yeah, yeah.
impactful for you to get in.
Yeah, sure, sure, sure. Monday I'll let you.
Okay,
Sure.
okay.
Okay.
All the best.
Thank you. Thank you.
Thank you. Okay, guys, I'll see you on Monday, and hopefully by Wednesday we wrap up NLP. Okay. Thank you. Keep practicing, and see you then. Have a happy weekend. Bye.